The North Pole feels permanent. It feels like one of those facts about reality that simply cannot change. You learn it as a child. You build maps around it. You navigate oceans, skies, and entire civilizations by trusting that it will always be there, pointing faithfully in the same direction. And yet, buried deep in the geological record is a quiet truth that feels almost unsettling. The North Pole does not stay put. Over long stretches of time, it has wandered, drifted, and on rare occasions, it has done something far more dramatic. It has swapped places entirely with the South Pole. North becomes south. South becomes north. The magnetic field that wraps our planet like an invisible shield flips itself inside out. At first glance, that sounds catastrophic. A planetary switch flipped the wrong way, a global malfunction, a recipe for extinction. But the truly unsettling part is not the reversal itself. It is what happens before it, because the danger does not arrive all at once. It creeps in slowly, quietly, over thousands of years, during a phase scientists call the build-up. Earth's magnetic field is generated deep below your feet, in a place you will never see. Beneath the crust and mantle lies a vast ocean of molten iron, churning endlessly around a solid inner core. As this electrically charged liquid metal moves, it creates currents. Those currents generate magnetism, and together they form the magnetic bubble that protects our planet from the constant stream of radiation pouring out of space. This system is called the geodynamo, and like any complex engine, it is not perfectly stable. Sometimes the flow becomes chaotic. The magnetic field weakens. It fragments. Multiple north poles can briefly exist at once. The field lines twist, stretch, and tangle like a spinning top beginning to wobble just before it falls. When this happens, the strength of Earth's magnetic shield can drop dramatically. In some cases, to a fraction of what it normally is. That is the build-up. During these periods, the planet becomes more vulnerable. Not unprotected, but exposed. Cosmic radiation that would normally be deflected begins to reach lower altitudes. Charged particles from the sun find easier pathways into the atmosphere. Auroras, once confined near the poles, can creep toward the equator, painting unfamiliar skies with strange colors. Satellites are among the first to notice something is wrong. Even today, there is a region over the South Atlantic where Earth's magnetic field is weaker than elsewhere. Satellites passing through this area are often forced to shut down sensitive electronics to avoid damage. Astronauts aboard the International Space Station have reported seeing flashes of light in their vision when high-energy particles pass through their eyes. Now imagine that weak spot expanding, spreading, enveloping much larger portions of the planet. Power grids become more susceptible to geomagnetic storms. Navigation systems begin to drift. Radio communications grow unreliable. Not overnight, not all at once, but gradually enough that the world must adapt in real time. And yet, despite how ominous this sounds, the story does not end in apocalypse. Earth has experienced magnetic reversals many times before, hundreds, possibly thousands. The last major reversal occurred roughly 780,000 years ago, and life did not vanish. Forests returned, animals evolved, humans eventually emerged, unaware that the planet beneath them had once rewritten its own invisible rules. This is why scientists remain cautious. A reversal is not an extinction event. It is a stress test. The real question is not whether Earth can survive a magnetic flip. It has already proven that it can. The question is whether a technologically dependent civilization can adapt quickly enough to a sky that behaves differently than the one it was built under. Right now, Earth's magnetic field is weakening. Measurements show that its overall strength has dropped over the past few centuries. The magnetic North Pole is drifting faster than it used to, sliding across the Arctic at an accelerating pace. These changes do not guarantee a reversal. The field has weakened and recovered before without flipping, but they do suggest that something is happening. And that uncertainty is where the tension lives. We are not standing on the edge of a switch labeled disaster. We are watching a complex system evolve, slowly, according to rules we are still trying to fully understand. The planet is not broken, it is dynamic. What makes this moment feel different is not the physics, it is us. For the first time in Earth's history, a species capable of observing a magnetic reversal may also be one that depends on fragile electronics, global infrastructure, and precise synchronization across the entire planet. We have wrapped our civilization around assumptions about stability, about consistency, about a sky that behaves predictably, and the universe has never promised that. This is not a story about panic. It is a reminder. Earth is not a static object drifting peacefully through space. It is alive with motion, energy, and long cycles that operate on timescales far beyond a human lifetime. The magnetic field that guides your compass is not a guarantee, it is a process. And like all processes in the cosmos, it can change. For centuries, Jupiter felt simple, massive, dominant, unmistakable. A colossal ball of gas sitting at the edge of the inner solar system, quietly shaping the orbits of everything around it. Textbooks described it with confidence. Diagrams showed a neat structure, clouds on top, gas beneath, and a dense, solid core anchoring the planet from within. It was a comforting picture, and it was almost certainly wrong. When scientists began looking at Jupiter more closely, the problem was not that the data was unclear. The problem was that the data refused to agree with the story we had already told ourselves. Every new measurement seemed to contradict another. Gravity behaved strangely. The planet's mass appeared unevenly distributed. Something deep inside Jupiter was blurring the lines between categories we thought were distinct. Gas, liquid, solid. Jupiter did not seem interested in choosing just one. The turning point came when a spacecraft named Juno arrived at Jupiter and began doing something deceptively simple. It listened. As Juno flew past the planet, Jupiter's immense gravity subtly altered the spacecraft's speed. Those changes were tiny, far smaller than a millimeter per second, but they were measurable, and embedded inside those shifts was a map of Jupiter's interior. Gravity does not lie. It reveals where mass truly lives. What Juno found unsettled decades of assumptions. Instead of a compact, well-defined core, the data pointed to something far stranger. Jupiter's center appeared smeared out, diffuse, spread across a region that extended to nearly half the planet's radius. Heavy elements were not confined to a tidy ball at the center. They were mixed upward, dissolving into layers above. Jupiter's core was not solid in the way we imagined. It was fuzzy. This discovery created an immediate problem because it challenged both of the dominant theories of how Jupiter formed. One model suggested that a solid core formed first, then pulled in gas from the surrounding disk. The other proposed that Jupiter collapsed directly from a dense region of gas, without a large core at all. Juno's data did not cleanly support either picture. A fuzzy core suggested a violent past. Perhaps early in Jupiter's history, massive impacts shattered an original core and stirred its contents into the surrounding layers. Or perhaps the core never fully solidified, existing instead as a gradient where materials slowly transition from one state to another under unimaginable pressure. At the heart of Jupiter, pressure climbs to millions of times that of Earth's atmosphere. Hydrogen, normally a simple gas, is squeezed into a metallic form. Electrons roam freely. The planet becomes an enormous, slowly churning dynamo, and that dynamo generates the most powerful magnetic field of any planet in the solar system. Here, gravity and magnetism are inseparable. Jupiter's magnetic field is not just strong, it is complex, lopsided, twisted. It does not emerge neatly from the poles the way Earth's field does. Instead, it erupts in patches, loops, and anomalies that hint at turbulent flows deep inside. Those flows are driven by heat. Jupiter radiates more energy than it receives from the Sun, a leftover glow from its formation and slow contraction. That heat rises, material moves, layers slide past one another, and the boundary between core and envelope becomes less of a line and more of a fog. Understanding that fog matters because Jupiter is not just another planet, it is a template. Gas giants are the most common type of large planet we have found beyond our solar system. If we misunderstand Jupiter, we misunderstand countless worlds orbiting distant stars, worlds that may host moons, worlds that may shape habitable environments, worlds that influence the architecture of entire planetary systems. Jupiter also played a crucial role in shaping our own cosmic neighborhood. Its gravity sculpted the asteroid belt, it deflected comets, it likely prevented excessive bombardment of the inner planets, giving life on Earth the breathing room it needed to evolve. But Jupiter is not a benevolent guardian. It is a force, and forces do not have intentions. The realization that Jupiter's interior is neither clean nor simple forces scientists to confront a deeper truth. Nature rarely draws sharp boundaries. It prefers gradients, transitions, states that blur rather than separate. This lesson echoes across the universe. Stars do not end neatly at their surfaces. Galaxies do not have crisp edges. Even planets, it seems, resist the categories we assign them. Jupiter exists in a perpetual in-between, between gas and liquid, between solid and fluid, between order and chaos. And we only noticed because we stopped looking at it as an image and started listening to how it pulls on space itself. The fuzzy core is not a failure of theory. It is a reminder of humility. The universe does not owe us simple explanations. It only offers clues, hidden in motion, gravity, and time. As Juno continues its passes, refining the map with every orbit, the picture grows richer and more confusing at the same time. Each answer opens new questions. How stable is this interior structure? How did it evolve? And what does it mean for planets even larger, orbiting stars far beyond our reach? Jupiter was never what we thought, not because we were careless, but because the truth is layered and patience is required to see it. We are learning to read planets the way the universe writes them, not in lines and labels, but in gradients and flows. And Jupiter, immense and ancient, is still teaching us how to listen. Every morning feels immediate. The sun rises, light floods the sky, shadows snap into place. It feels as though sunlight arrives the instant it is created, racing across space at an unstoppable speed and reaching your eyes just 8 minutes after leaving the sun's surface. That part is true. What is not true is where that journey actually begins. Deep inside the sun, far below the glowing surface you see, energy is born in violence. At the core, temperatures climb into the tens of millions of degrees. Pressure crushes matter so intensely that atomic nuclei are forced together. Hydrogen fuses into helium. Mass becomes energy. This is nuclear fusion, the engine that has kept the sun shining for billions of years. When fusion occurs, energy is released in the form of gamma rays. These are not gentle particles of light. They are the most energetic photons the universe can produce. And the moment they are created, their journey begins. But this journey does not go where you think. A gamma ray born in the sun's core does not shoot straight outward. It does not race directly to the surface and escape. Instead, it collides almost immediately with nearby particles. It is absorbed, re-emitted, scattered. Its direction changes. Its energy drops. Over and over again, the photon begins a slow, chaotic crawl. Inside the sun, matter is packed densely. Atomic nuclei and electrons fill the space like an impossibly crowded room. A photon can travel only a tiny distance before hitting something else. Each collision knocks it off course. Each interaction robs it of energy. Gamma rays become X-rays. X-rays become ultraviolet. Ultraviolet becomes visible light. This process is called a random walk, and it is anything but fast. For a single photon, the journey from the core of the sun to its surface can take hundreds of thousands of years. Some estimates stretch even longer. During that time, the photon is not a single, identifiable object. It is constantly being transformed, passed along, recreated. Its original identity dissolves into a chain of interactions. By the time light finally reaches the sun's visible surface, the photosphere, it has forgotten where it came from. And then, suddenly, everything changes. Once a photon escapes the sun's surface, it enters space. There, the density drops dramatically. collisions become rare. The photon accelerates to the ultimate speed limit of the universe. In just over 8 minutes, it crosses 93 million miles and reaches Earth. From your perspective, sunlight feels immediate, but in truth, it is ancient. The light warming your skin today began its journey long before human civilization existed, before agriculture, before cities, before language as we know it. That energy was locked inside the sun, wandering aimlessly through plasma, waiting for its chance to escape. The sun itself is layered, and each layer tells part of this story. Above the core lies the radiative zone, where energy moves almost entirely through this slow photon diffusion. It is a place of patience, a region where time stretches, where nothing moves quickly, despite the immense heat. Above that is the convective zone. Here, the rules change. Hot plasma rises, cooler plasma sinks. Massive columns of material churn like boiling water in a pot. Energy is carried not by photons alone, but by motion, by bulk movement of matter itself. This convective motion is what creates the sun's surface patterns, granules, cells, bright and dark regions constantly forming and dissolving. It is also what helps generate the sun's magnetic field, twisting and stretching invisible lines of force that can snap and reconnect in sudden bursts. Those bursts are solar flares, coronal mass ejections, explosions that fling charged particles across the solar system. The same sun that nurtures life can also disrupt it. When eruptions occur, Earth's magnetic field acts as a shield, deflecting much of the incoming radiation. But some particles slip through, spiraling down toward the poles and igniting auroras. Curtains of light dance across the sky, silent evidence of a star reaching across space and touching our atmosphere. And still, beneath all of this activity, the slow photon journey continues. The sun is stable not because nothing happens, but because countless processes balance one another. Fusion pushes outward, gravity pulls inward, energy struggles to escape, structure emerges from tension. This balance will not last forever. Over billions of years, the sun's core will change. Hydrogen will grow scarce. Fusion will shift. The sun will swell into a red giant, altering the fate of every planet in its path. But even then, photons will still begin their long walk outward, carrying energy forward through time. There is something deeply humbling about this realization. We tend to think of stars as instant sources of light, as though they simply turn on and shine. In reality, a star is a memory machine. It stores energy, delays it, releases it long after its origin. Every ray of sunlight is a message from the past, delayed by the physics of matter and motion. When you stand under the sun, feeling its warmth, you are not just experiencing a moment. You are touching a process that began hundreds of thousands of years ago, deep in a place no probe will ever reach. The sun does not rush. It does not need to. Its light arrives exactly when it means to, and that quiet patience, hidden beneath the brightness of day, is one of the most profound truths written into the fabric of our star. When you look up at the night sky, the Milky Way appears familiar, a pale band of light stretching across darkness, a quiet river of stars arching overhead. For most of human history, that glowing stripe was the entire galaxy as far as our eyes were concerned. But what you see is not the galaxy. It is a fragment. Between the stars and your eyes lies a veil of dust. Fine grains of carbon, silicon, and ice drift through interstellar space, absorbing and scattering visible light. They erase vast regions of the Milky Way from view, hiding its true structure behind darkness. Entire star-forming regions vanish. The crowded heart of the galaxy becomes a blur. For a long time, we accepted this blindness as a limitation we could not overcome. Then we changed how we looked. Instead of relying on visible light, astronomers turned to infrared. Longer wavelengths slip past dust grains more easily, revealing objects that were previously invisible. Where optical telescopes see emptiness, infrared instruments uncover staggering complexity. One of the most ambitious efforts to map the hidden Milky Way came from a telescope perched high in the Chilean Andes. Its mission was simple in principle and monumental in scale. Survey the galaxy in infrared. Catalog its stars. Reveal its bones. The result was a map unlike anything humanity had ever created. Instead of millions of stars, it revealed more than 1 billion. Dense clusters emerged where darkness once ruled. Star-forming nurseries appeared as glowing knots embedded in vast clouds of gas. Filaments of structure traced the spiral arms in greater detail than ever before. The Milky Way began to look less like a flat disk and more like a living system, tangled and layered. At the center of it all lies a region we cannot see directly, even in infrared. The galactic core is so crowded, so chaotic, that individual stars blur together. And yet, their collective motion tells a story. Stars orbit something massive and unseen, something compact, something with gravity so intense that space itself bends around it. A supermassive black hole. It sits at the heart of the Milky Way, containing millions of times the mass of the Sunday. It does not shine. It does not announce itself. It reveals its presence only through its influence on everything around it. And still, this black hole is only one piece of the puzzle. The infrared map showed that the Milky Way is not symmetrical. One spiral arm is longer than the other. The stellar bar at the center is tilted, not aligned cleanly with the disk. Streams of stars arc through space, remnants of smaller galaxies torn apart and absorbed over billions of years. Our galaxy is a survivor. It has grown by collision, by merger, by slow gravitational cannibalism. Each encounter left scars, now visible as faint trails of stars stretching across the halo. Even our own sun is part of this story. It drifts through the galaxy at tremendous speed, completing one orbit around the center every few 100 million years. During that journey, it passes through spiral arms, molecular clouds, and regions of varying stellar density. The sky above Earth is not fixed. It evolves. Infrared surveys also revealed something subtler. The Milky Way is filled with cold stars, small, dim objects that emit little visible light but glow softly in infrared. Red dwarfs, brown dwarfs, failed stars that never ignited full fusion. These objects are everywhere. They dominate the stellar population by number, quietly shaping the galaxy's mass without ever shining brightly in the sky. The galaxy you see with your eyes is biased. It favors the loud, the hot, the massive. The galaxy revealed in infrared is democratic. It shows everything. And that matters, because understanding the true distribution of mass in the Milky Way helps explain how it moves, how its spiral arms persist, how its disk remains stable, how dark matter may be woven through its structure, guiding motion without emitting light of its own. This hidden galaxy forces a re-evaluation of our place within it. We are not near the center. We are not in a privileged location. We orbit quietly, embedded in one spiral arm among many, surrounded by stars we cannot see without technological extensions of our senses. The Milky Way is not a backdrop. It is an environment. And environments influence what can exist within them. Star formation depends on density and motion. Planet formation depends on available elements forged in earlier generations of stars. Even the likelihood of catastrophic events depends on where a system resides within the galactic web. By peeling back the dust, infrared astronomy has transformed the Milky Way from a vague smear of light into a dynamic ecosystem, one that breathes, one that evolves, one that carries the memory of billions of years of change in the motion of its stars. And perhaps the most unsettling realization of all is this. For nearly all of human history, this galaxy was here, unchanged in its vast structure. While we knew almost nothing about it, we named constellations, we told stories, we navigated by points of light. All the while, the true shape of our cosmic home remained hidden, waiting for us to learn how to see. The Milky Way did not change. We did. When you look up at the night sky now, remember that what you see is only a surface. Beneath it lies a deeper reality, written in wavelengths your eyes cannot detect, a galaxy rich with motion, memory, and hidden light. And we are finally learning how to read it. It feels natural to ask where the universe began. Every explosion you have ever seen starts somewhere. A firework blooms from a single point. A shockwave spreads outward from a source. Cos comes first, then motion follows. When we hear the words Big Bang, the mind immediately searches for a location, a center, a place where everything started and from which all things moved away. But the universe does not work that way. The Big Bang was not an explosion in space. It was an expansion of space itself. And that single distinction changes everything. To understand this, you have to abandon the idea of the universe as something sitting inside a larger emptiness. There was no surrounding void, no external stage. Space did not expand into anything. Space expanded, full stop. Every region of the universe was once compressed into a hotter, denser state, not gathered at one point, but everywhere at once. That means there is no cosmic center to point to, no special location where the Big Bang happened more. Wherever you are, that place was once part of the early universe. The same is true for every galaxy, every star, every atom. The Big Bang happened here, and here, and there. This idea is deeply counterintuitive because our brains are built to understand motion through space, not the expansion of space itself. But the mathematics is unambiguous. When astronomers observe distant galaxies, they see them moving away from us. The farther away a galaxy is, the faster it recedes. This is not because we occupy a privileged position. It is because space between galaxies is stretching. If observers lived in another galaxy, they would see the same thing. Every direction would appear to be expanding away from them. They too would feel as though they were at the center, and yet no one is. The best analogy is not an explosion, but a surface that grows. Imagine points painted on the surface of an inflating balloon. As the balloon expands, every point moves away from every other point. There is no center on the surface itself. The expansion is internal. The universe behaves like that surface, but in 3 dimensions. This realization reshapes how we think about beginnings. The early universe was not a fireball erupting outward from a single location. It was a hot, dense state everywhere, cooling as space expanded. As it cooled, simple particles formed, then atoms, then clouds of gas. Then the first stars ignited, ending the cosmic dark ages. Light from that early time still fills the universe today. It appears as a faint glow called the cosmic microwave background. This radiation is remarkably uniform in every direction, with only tiny variations. Those variations are important. They represent the earlier seeds of structure, small density differences that gravity later amplified into galaxies and clusters. There is no brighter spot in that background marking a center, no gradient pointing to an origin. The pattern is the same no matter where you look. The universe does not remember a center because it never had one. Even time behaves differently near the beginning. As we trace the expansion backward, temperatures rise, densities increase. The equations describing the universe eventually break down. This breakdown is not proof of a literal singular point in space, but a sign that our current understanding of physics is incomplete. We do not yet know what happened at the very earliest moments. Whether the universe emerged from a quantum fluctuation, whether time itself had a beginning, whether the Big Bang was a transition from an earlier phase rather than a true start. What we do know is that asking where it happened is the wrong question. The more accurate question is how it happened. And that question leads to something even more unsettling. If the universe has no center, then it also has no edge in the way we imagine. There is a limit to what we can see, set by the age of the universe and the speed of light. Beyond that horizon, space continues. Galaxies exist that we will never observe, not because they are hidden, but because their light will never reach us. Our observable universe is not the whole universe. It is a bubble carved out by time. From within that bubble, everything appears ordered around us. The sky looks isotropic. Expansion looks symmetrical. This can give the illusion of centrality, but it is an illusion born of perspective. There is something profoundly humbling about this. Humans have a long history of placing themselves at the center of things, at the center of the earth, at the center of the solar system, at the center of the cosmos. Modern cosmology removes that comfort entirely. We are not central in space. We are not central in time. We exist during a fleeting era, in a galaxy among hundreds of billions, in a universe that does not orient itself around us in any meaningful way. And yet, paradoxically, the universe is intimate, because wherever you are, you occupy a valid reference frame. The laws of physics work the same. The expansion looks the same. The cosmic story includes you fully, not as a privileged observer, but as a participant. The absence of a center does not make the universe empty or indifferent. It makes it shared. Every place carries the same origin. Every region traces its history back to the same early conditions. The atoms in your body were forged in stars that formed long after the Big Bang, but the space between those atoms has been stretching since the universe was young. You are built from matter shaped by ancient expansion. The universe did not begin somewhere else and arrive here later. It began here, and here grew into everything else. When you imagine the Big Bang now, do not picture a point. Picture a moment, a transition, a change in state that affected all of space at once. There is no arrow pointing back to a center you could ever reach. There is only history written everywhere, and that may be the strangest truth of all. By now, the universe may feel unsettlingly vast. A planet whose magnetic field can rewrite itself. A gas giant with no clear boundary between solid and fluid. A star whose light takes hundreds of thousands of years to escape. A galaxy hidden behind dust. A universe with no center at all. It is tempting to think that reality is chaotic, unstable, that beneath the surface, everything is constantly on the verge of falling apart. But the deeper physicists look, the more they encounter something unexpected. Rules. Not rules written anywhere, not instructions handed down, but relationships so consistent, so precise, that the universe seems to lean on them everywhere at once. These rules do not care where you are. They do not weaken with distance. They do not change with time, as far as we can tell. They simply hold. Take gravity. It shapes planets, stars, galaxies, and the large-scale structure of the universe. It curves space and slows time. It guides the motion of light itself. And yet, gravity is astonishingly weak. Compared to the other fundamental forces, it is almost negligible at small scales. A simple magnet can lift a paperclip against the gravitational pull of the entire Earth, and still, gravity dominates the cosmos. It does so not by strength, but by persistence. Gravity only attracts, it never repels. Over enormous distances and long stretches of time, that quiet pull adds up. Small irregularities grow, clouds collapse, stars ignite, galaxies assemble. Gravity is patient. The same patience appears in other laws as well. The speed of light remains constant, no matter how fast you move. Energy is conserved, changing form but never vanishing. Entropy increases, pushing systems toward disorder, even as local pockets of complexity briefly emerge. These principles apply everywhere we look, from the smallest particles to the largest cosmic structures. And this universality raises a profound question. Why should the universe obey the same rules everywhere? Why should a galaxy billions of light years away behave according to the same physics as an atom in your body? There is no obvious reason that it must. Yet, observation after observation confirms it. Spectral lines from distant stars match those measured in laboratories on Earth. The behavior of light near black holes follows the same equations that describe light bending around the sundial. The cosmic microwave background carries patterns that align perfectly with predictions based on simple physical assumptions applied to the early universe. Reality appears stitched together by consistency. This consistency is what makes science possible. Without it, there would be no way to infer unseen processes from limited data, no way to connect experiments performed here and now to events unfolding across the cosmos. And yet, consistency does not mean simplicity. The laws themselves are elegant, but their consequences are wildly rich. From a small set of rules emerges staggering diversity: spiral galaxies and elliptical ones, rocky planets and gas giants, calm stars and explosive ones, life and lifelessness. The universe does not need special instructions for each outcome. It lets complexity arise naturally from repetition and scale. This is both reassuring and unsettling. Reassuring, because it means the universe is understandable, at least in principle, that beneath the noise and motion, there is structure. Unsettling, because those same rules are indifferent. They do not care about outcomes. They do not favor stability over destruction or life over emptiness. They simply operate. Stars burn until fuel runs out. Planets cool. Orbits decay. Even galaxies will eventually drift beyond one another's reach as expansion accelerates. The universe is lawful, but not gentle. And yet, here we are. Conscious systems have emerged within this framework. Matter has organized itself into beings capable of asking why these rules exist at all, capable of measuring them, questioning them, testing their limits. This may be the most remarkable consequence of physical law. Not that it produces stars or galaxies, but that it allows for curiosity. We are part of the universe trying to understand itself, using tools shaped by the very rules we are studying. Our thoughts arise from electrical signals governed by physics. Our instruments obey the same constraints as distant quasars and ancient photons. There is no separation between observer and observed at a fundamental level. This realization blurs boundaries. When you learn about cosmic expansion, you are not learning about something distant and abstract. You are learning about the behavior of the space inside your own atoms. When you learn about entropy, you are learning about the arrow of time that shapes your memories. When you learn about gravity, you are learning about the same force that keeps your feet on the ground and binds galaxies together. The universe is not out there. It is here, held together by quiet rules that do not announce themselves, but never stop acting. As our understanding deepens, new questions emerge. Are these laws truly fundamental, or are they consequences of deeper principles we have not yet discovered? Could they have been different? Do other regions of a larger reality obey other rules entirely? We do not yet know. What we do know is that the universe we inhabit is balanced on a knife edge of consistency. Slight changes in these rules could prevent stars from forming, or chemistry from working, or complexity from emerging at all. That fact has led some to wonder whether our universe is special. Others argue that, if many universes exist, we naturally find ourselves in one compatible with observers, a selection effect rather than a design. At present, these ideas remain speculative, but they highlight something important. The more we learn about the universe, the less it feels random, and the less it feels designed. Instead, it feels inevitable. As though once the rules were set, everything that followed was a long, unfolding consequence. From those consequences came planets, stars, galaxies, and eventually, questions. The universe does not speak, it does not explain itself, but it leaves patterns. And by following those patterns, patiently, we get closer to understanding not just where we are, but what kind of reality could give rise to beings who wonder about it at all. Time feels obvious. It moves forward. Moments stack neatly behind us. The past is fixed, the future open, the present razor thin and fleeting. We experience this flow so intimately that questioning it feels almost pointless. Time is simply there, carrying everything along. And yet, modern physics suggests that this familiar picture may be deeply misleading. When Albert Einstein reshaped our understanding of gravity, he did something far more radical than replace a force with curved space. He fused space and time into a single structure, space-time, a four-dimensional fabric in which distance and duration are inseparable. In this framework, time does not flow in the way we perceive it. It exists as a dimension, similar to space, woven into the geometry of the universe. Objects do not move through time because time pushes them forward. They move because they follow paths through space-time, shaped by mass and energy. This idea leads to consequences that strain intuition. Clocks tick at different rates depending on speed and gravity. A clock on a satellite runs faster than one on Earth's surface. A clock near a massive object runs slower than one far away. These effects are not theoretical. They are measured daily. Without correcting for them, global navigation systems would drift out of sync within hours. Time is flexible, but relativity goes even further. In Einstein's equations, there is no universal present, no single moment that the entire universe agrees upon as now. Events that appear simultaneous to one observer may occur at different times for another observer moving differently through space. This destroys the idea of a shared cosmic clock. Instead, every observer carries their own time, shaped by their motion and environment. The universe does not privilege one perspective over another. All frames are equally valid. From this emerges a disturbing possibility. If space-time exists as a whole, then the past and future may be just as real as the present. This idea is known as the block universe. In this view, time does not flow, it simply is. Every moment exists, laid out within space-time. Like frames in a film reel, you experience those frames in sequence, but the sequence itself may not be fundamental. The future may already exist, just as fixed as the past. Your sense of becoming, of moving forward, could be a feature of consciousness rather than reality. This does not mean free will is an illusion in any simple sense. It means that freedom, choice, and causation may be embedded within a larger structure that does not privilege one moment as more real than another. Physics does not yet tell us how to reconcile this picture with human experience. Quantum mechanics complicates the story further. At the smallest scales, events appear probabilistic. Outcomes are not determined until measurements occur. Some interpretations suggest that the future is genuinely open until observed. Others suggest that all outcomes exist simultaneously, branching into multiple histories. Time, in these frameworks, becomes even stranger. Some equations in fundamental physics do not distinguish between past and future at all. They work equally well forwards and backwards. The arrow of time, the sense that causes precede effects, seems to emerge not from basic laws, but from statistics. From entropy. Entropy measures the number of ways a system can be arranged. Systems naturally evolve from ordered states to disordered ones because disorder is overwhelmingly more likely. A broken glass can shatter in countless ways. It can reassemble in essentially none. This statistical tendency gives time a direction. The early universe was remarkably ordered. Low entropy. As the universe expanded, entropy increased. Structures formed, stars burned fuel, energy spread out. That progression defines what we call the past and the future. Time's arrow may be less about motion and more about memory. We remember the past because entropy was lower then. Records could form. Information could be stored. The future, with higher entropy, has not yet created those records. In this sense, time feels real because we are creatures built to process information in one direction. This idea is unsettling, but also clarifying. It suggests that time is not a river carrying us along, but a landscape we traverse in a particular way. Consciousness may be the process that stitches moments together into a story. Physics describes the terrain. Experience describes the journey. Whether time truly flows, or whether that flow is an emergent illusion, remains one of the deepest open questions in science. Experiments continue. Theories evolve. No consensus has been reached. But one thing is clear. Time is not what common sense suggests. It bends. It stretches. It fragments. It may even exist all at once. And yet, despite all of this strangeness, your experience of time still matters. It is the context in which meaning arises. Decisions matter because they are made within a sequence. Stories matter because they unfold. Physics may describe a timeless structure, but life is lived moment by moment. Perhaps both are true. The universe may be a static space-time block, and within it, conscious beings trace paths that feel dynamic, urgent, and real. If so, then the mystery of time is not just a question about the cosmos. It is a question about us, about why the universe, governed by impersonal laws, gives rise to perspectives that feel time passing, futures approaching, and moments slipping away. Time may be an illusion, but it is an illusion powerful enough to shape everything that has ever happened, and everything that ever will. There is a moment in modern physics when intuition finally breaks. It happens when you realize that observing the universe is not a passive act. Looking does not simply reveal what is already there. At the deepest levels of reality, observation appears to participate in what becomes real. This idea did not emerge from philosophy, it came from experiment. When physicists began probing matter at extremely small scales, they encountered behavior that defied classical explanation. Particles acted like waves. Waves acted like particles. Objects seemed to exist in multiple states at once, only committing to a definite outcome when measured. This strange behavior is captured by quantum mechanics. At the heart of quantum theory lies a mathematical object called the wave function. It does not describe a particle's position or momentum directly. Instead, it encodes probabilities. It tells you what might happen if you look. Before measurement, a quantum system exists in a superposition. Multiple possibilities coexist simultaneously. A particle can be here and there. A property can have different values at the same time. This is not metaphorical. It is how the equations work. Then measurement occurs. When a system is observed, the wave function appears to collapse. One outcome becomes real, the others vanish. Probability gives way to fact. This raises an unavoidable question. What counts as an observation? Is it a human looking at an instrument? Is it a detector registering a signal? Is it any interaction with the environment? At what point does possibility harden into reality? There is no universally accepted answer. Some interpretations suggest that observation is nothing special, that interactions with the environment cause quantum systems to decohere, losing their superpositions without any need for consciousness. Reality becomes classical through entanglement with countless degrees of freedom. Other interpretations are more unsettling. They suggest that the wave function never truly collapses, that all possible outcomes occur, branching into separate, non-interacting histories. In this view, the universe constantly splits, producing an ever-growing multiverse. You experience one branch, others exist beyond reach. There are also interpretations that place consciousness closer to the center of the mystery. They argue that measurement requires awareness, that reality only becomes definite when it is experienced. These ideas remain controversial. What is not controversial is that quantum mechanics works. Its predictions are confirmed to extraordinary precision. Technologies based on it power modern civilization. Transistors, lasers, magnetic resonance imaging, and atomic clocks all rely on quantum principles. Reality behaves this way whether we like it or not. The tension lies in interpretation. Quantum theory describes outcomes, not meaning. It gives probabilities, not pictures. When physicists try to translate its mathematics into a story about what is really happening, disagreement begins. This is where the discomfort grows, because quantum mechanics seems to blur the boundary between observer and observed. It challenges the idea that the universe has definite properties independent of measurement. It suggests that at fundamental scales, reality may be relational rather than absolute. Properties exist only in context. This does not mean the universe depends on humans. Observations occurred long before observers evolved. Stars formed, atoms combined, structure emerged. But it may mean that interactions, not objects, are primary. Particles do not carry fixed attributes waiting to be revealed. They participate in relationships. Measurement is one such relationship. From this perspective, the universe is not made of things, but of events. This view aligns strangely well with relativity, where space and time are not fixed backgrounds but dynamic participants. It also echoes ideas in cosmology, where large-scale structure emerges from tiny fluctuations amplified over time. Across scales, reality appears less like a collection of solid objects and more like a web of processes. This realization forces a reconsideration of objectivity. Science has always aimed to describe the universe as it is, independent of who observes it. Quantum mechanics complicates that goal, not by undermining rigor, but by redefining what independence means. Observers cannot be fully removed from the description because observation is part of the physical process. This does not make science subjective. It makes it relational. And that distinction matters. It means that knowledge is not about standing outside the universe and looking in. It is about participating within it, using interactions governed by the same laws we seek to understand. We are not detached spectators. We are embedded. This embedding may explain why quantum mechanics feels so alien. Our intuitions evolved to navigate a world where objects have definite positions and histories. They did not evolve to grasp superpositions or entanglement. Yet the universe does not adjust itself to human comfort. Entangled particles can influence one another instantly across vast distances, not by sending signals, but by sharing a single quantum state. Measurements performed here affect outcomes there, even when no information travels between them. This phenomenon disturbed Einstein deeply. He called it spooky action at a distance. Experiments have repeatedly confirmed it. Entanglement does not allow faster than light communication. Causality remains intact, but it does reveal that separateness is not as fundamental as it seems. At the deepest level, the universe may be less like a collection of independent pieces and more like a single, interconnected whole. This idea resonates beyond physics. It echoes in cosmology, where every region traces back to the same early conditions. It echoes in biology, where life depends on networks of interaction. It echoes in human experience, where meaning arises through relationships. Quantum mechanics does not tell us what to feel about this. It simply tells us that reality is stranger, more subtle, and more interconnected than classical pictures suggest. Observation does not merely reveal the universe. It is one of the ways the universe happens. And that realization quietly reshapes what it means to ask questions, to seek answers, and to understand our place within a reality that cannot be fully separated from the act of understanding itself. There is a limit built into the universe, not a wall, not a boundary you could ever reach, but a horizon defined by time itself, a distance beyond which information can never arrive, no matter how long you wait or how powerful your instruments become. This limit is called the cosmic horizon. When you look out into space, you are also looking back in time. Light takes time to travel, and the universe has existed for a finite duration. That means there is a maximum distance from which light has had time to reach us since the beginning of cosmic expansion. Beyond that distance, events may be happening right now that we will never see, not because they are hidden, but because the universe is expanding in such a way that their light will never catch up. This idea feels unsettling because it places a permanent boundary on knowledge. No future technology, no clever workaround, no patience measured in billions of years can overcome it. Some parts of reality are simply out of reach. At present, the observable universe spans a region tens of billions of light years across. Within it lie hundreds of billions of galaxies, each containing hundreds of billions of stars. It is already overwhelming in scale, and yet this vast domain may represent only a tiny fraction of what actually exists. Space beyond our horizon continues. Galaxies form there, stars ignite, planets orbit, perhaps life emerges, perhaps entire civilizations rise and fall, all without any possibility of interaction with us. This is not speculation in the loose sense. It follows directly from the equations that describe cosmic expansion. Space itself is stretching, and in distant regions it is stretching so rapidly that light emitted there will never traverse the growing distance between us. Those regions are not frozen in time. They are not paused. They are simply causally disconnected. The universe does not end at the horizon. Our access to it does. This distinction matters. It means that, when we describe the universe, we are always describing a sample, a region bounded by what light has had time to show us. Beyond that, we must infer cautiously, guided by physical principles but aware of the limits of confirmation. Cosmology, then, is an exercise in humility. We build models that explain what we can see. We test them against observation. When those models work, we tentatively extend them beyond the observable domain, not because we know they apply there, but because consistency suggests they might. The horizon reminds us that certainty has edges. There is another horizon as well, even stranger. As the expansion of the universe accelerates, driven by dark energy, distant galaxies will gradually slip beyond our observable reach. Light emitted from them today may still arrive. Light emitted in the future will not. Over unimaginably long timescales, the universe will appear to grow emptier. Galaxies outside our local group will fade from view. The cosmic microwave background will stretch to wavelengths so long they are undetectable. Evidence of the Big Bang itself will disappear. Future observers, if any exist, may see a quiet universe containing only a handful of galaxies. They may have no direct observational proof that a hot, dense beginning ever occurred. Cosmic history will be erased by expansion. This is not because the universe forgets. It is because information disperses beyond reach. The arrow of time and the limits of observation intertwine. The horizon is not just a spatial boundary, it is a temporal one. It separates what can influence us from what cannot, what can be known from what must remain hypothetical. And yet, even within these limits, the universe has left clues. The uniformity of the cosmic microwave background, the distribution of galaxies on large scales, the abundance of light elements. Together, these observations point to a shared origin, a common early state. They suggest that regions now far beyond one another were once close enough to interact. This raises a profound puzzle. How did distant regions of the universe become so similar if they are now causally disconnected? The leading explanation involves a brief period of rapid expansion early in cosmic history, called inflation. During this phase, space expanded exponentially, stretching tiny regions to enormous scales. Areas that were once in contact were flung far apart. Inflation explains why the universe appears uniform on large scales and why small quantum fluctuations were amplified into the seeds of galaxies. But inflation also deepens the mystery. Some versions of the theory suggest that inflation never fully ends, that it continues in some regions, spawning countless expanding universes, each with its own properties. In this picture, our observable universe is one bubble among many. We cannot observe the others. We cannot interact with them. Their existence may forever remain beyond empirical test. This idea is controversial. Some physicists see it as a natural consequence of inflationary models. Others worry that it stretches the definition of science by invoking entities that cannot be observed. The debate is ongoing. What is clear is that the horizon forces difficult questions about what it means to explain something. Is a theory meaningful if it describes regions we can never see? Does explanatory power require testability everywhere, or is consistency within the observable domain enough? These questions do not have easy answers. They sit at the boundary between physics and philosophy, where mathematics meets meaning. The universe does not guarantee that all truths are accessible. It does not promise that every question has an answer we can reach. And yet, within our horizon, the cosmos is astonishingly generous. It offers patterns, regularities, and laws that allow a finite mind to grasp something of infinite scope. We cannot see everything, but we can see enough to know that what lies beyond is governed by the same deep principles. The horizon does not diminish the universe. It sharpens it. It reminds us that knowledge is contextual, bounded, and precious. That understanding arises not from omniscience, but from careful inference within limits. We live inside a cosmic window. Everything we know about the universe has arrived through that opening, carried by ancient light, stretched thin by expansion, shaped by gravity and time. Beyond the window, reality continues, indifferent to whether it is observed. The universe is larger than what we can know, and that fact does not make our understanding meaningless. It makes it remarkable that we understand anything at all. It is easy to imagine the universe as timeless. Stars burn for billions of years. Galaxies drift and collide on scales so vast that human history barely registers. Cosmic expansion unfolds so slowly that its effects are invisible across a lifetime. Against that backdrop, our moment feels insignificant. And yet, there is something profoundly unusual about now. We live during a narrow window in cosmic history, when the universe is both old enough to have formed complex structures and young enough for those structures to still be visible. a moment when stars shine brightly, galaxies cluster together, and the echoes of the Big Bang are still detectable in the sky. This balance will not last. In the distant future, the universe will look very different. Star formation will slow and eventually cease as galaxies exhaust their gas. Existing stars will burn out, leaving behind remnants, white dwarfs, neutron stars, black holes. Space will grow darker. Expansion will continue to accelerate. Galaxies beyond our local group will slip permanently beyond the cosmic horizon. The night sky will empty. Observers living in that far future, if any exist, may see a universe that appears static and small. They may find no evidence of cosmic expansion, no background radiation, no clear trace of a beginning. The universe will not have changed its history, but it will have hidden it. This realization gives our era a strange significance. We exist at a time when the universe is readable, when its past is written clearly across the sky, accessible to careful observation. We can see distant galaxies receding. We can measure the cooling glow of the early universe. We can reconstruct a timeline stretching back billions of years, all the way to the first fractions of a second. This is not guaranteed for all observers. The universe is not obliged to reveal itself. Our ability to understand cosmology depends not only on intelligence and technology, but on timing. We arrived early enough to catch the universe in the act of telling its story. That story is not gentle. It includes violent beginnings, explosive star deaths, galaxy collisions, and long eras of darkness. But it also includes subtle balances that allow complexity to arise. Heavy elements forged in stellar cores, stable planetary systems, chemical pathways that lead to life, biological evolution unfolding over billions of years. None of this was inevitable. Slight changes in cosmic conditions could have prevented it entirely. If expansion had been faster, matter might never have clumped. If it had been slower, the universe could have collapsed before stars formed. If fundamental constants differed even slightly, chemistry might fail. We live in a universe that permits structure, and we live at a time when that structure is abundant. This has led to deep philosophical questions. Is this coincidence? Necessity? Selection? Some argue that many universes exist, each with different properties. We find ourselves in one compatible with observers, because no one exists in the others to ask the question. Others suggest that the laws of physics uniquely determine the universe we see, that no alternatives are possible. At present, these ideas remain unresolved. What is clear is that our moment is fleeting. On cosmic timescales, the era of bright galaxies and accessible information is brief, a thin slice between a hot, opaque beginning and a cold, empty future. And within that slice, conscious beings have emerged. We are not separate from the universe's evolution. We are a consequence of it. Matter organized itself into stars. Stars forged elements. Elements assembled into planets. And on at least one of those planets, matter learned to think. This perspective can feel overwhelming. It collapses the distance between cosmology and personal experience. Your existence is not an accident layered on top of the universe. It is part of the same process that drives expansion, star formation, and entropy increase. The universe is not static scenery. It is an unfolding event, and we are participants. This does not mean the universe cares about us. It means that caring itself is one of the things the universe can do under the right conditions. There is something fragile about this realization, not because life is rare, though it may be, but because awareness depends on a narrow range of circumstances. It requires energy flows, stability, and time. It requires stars that burn steadily, planets that remain hospitable, and histories that avoid catastrophe long enough for complexity to build. These conditions will not persist forever. The sun will change. Earth will become uninhabitable. Humanity's future, if it has one, lies beyond this planet, beyond this era, and yet, right now, we can look up and see a sky filled with information. We can measure the universe's age. We can trace our origins to stellar furnaces. We can test theories against observation and refine them when they fail. We can ask questions that the universe is still capable of answering. That is extraordinary. It suggests that meaning does not require permanence, that significance can arise in transient moments, that a brief window of understanding is enough to matter. The universe may not remember us, but we can remember the universe. We can piece together its story, not because it was designed for us to do so, but because the same laws that govern its expansion also permit minds to emerge and reflect. In this sense, knowledge is not separate from cosmology. It is one of its outcomes. We are living during the universe's readable phase, a moment when stars still shine, signals still reach us, and the past has not yet faded beyond detection. This moment will pass, but while it lasts, it offers something rare: the chance to understand where we are, what kind of reality we inhabit, and how a universe governed by impersonal laws can give rise to beings who care about truth. That opportunity is fragile, and it is now. There is a question that sits quietly beneath every scientific discovery: not how something works, not when it began, not where it is headed, but why a universe governed by blind, impersonal laws should produce beings capable of asking questions in the first place. Physics does not require curiosity. Equations function perfectly well without observers. Stars will fuse hydrogen whether or not anyone notices. Galaxies will collide without witnesses. Expansion will continue in silence. And yet, here we are. The universe has generated structures complex enough to reflect on the universe itself. This is not a trivial fact. For most of cosmic history, nothing could ask questions. The early universe was hot, dense, and simple. Particles interacted, atoms formed, light streamed freely. But there was no awareness, no memory, no meaning attached to events. Then, gradually, complexity emerged. Gravity gathered matter into stars. Stars forged heavier elements. Supernovae scattered those elements into space. Planets formed. Chemistry diversified. On at least one world, molecules learned to copy themselves. Life began. Even then, awareness was not guaranteed. Life can exist without understanding. For billions of years, it did. Single cells replicated. Multicellular organisms evolved. Ecosystems stabilized and collapsed. Intelligence, when it appeared, was narrow and practical. Awareness served survival, not contemplation. The universe remained largely unexamined. Only very recently did something unusual happen. A species arose that could model reality abstractly, that could imagine events it had never witnessed, that could test ideas against observation and discard those that failed, that could look at the sky and ask not only what it contained, but why it existed at all. This transition did not require new physical laws. It required scale. Neurons operate according to the same physics as stars and atoms. Electrical signals follow well-understood principles. Chemical gradients behave predictably. There is nothing supernatural in thought itself. And yet, when enough matter is arranged in the right way, something qualitatively different appears. Experience, a point of view. This raises a profound tension. On one hand, humans are not special in any cosmic sense. We occupy no central position. We live on an ordinary planet orbiting an average star in a typical galaxy. The universe does not revolve around us. On the other hand, the universe has produced at least one location where it can be studied, measured, and understood. That is not privilege. It is emergence. Some philosophers and physicists describe this as the universe becoming self-aware, not in a mystical sense, but in a functional one. Information processed by matter arranged by cosmic evolution. From this perspective, consciousness is not an intrusion into physics. It is a consequence of it. The same laws that govern expansion and entropy also permit localized decreases in entropy, where energy flows allow complex structures to form temporarily. Life exploits those flows. Intelligence builds on life. Understanding emerges from intelligence. None of this violates physical law. It rides on it. This realization reframes the relationship between observer and universe. We are not outside reality looking in. We are part of reality looking at itself. When astronomers measure distant galaxies, they are not peering into a separate realm. They are using matter forged in stars to study other stars. When physicists probe quantum fields, they are using interactions governed by those same fields. Knowledge is recursive. The universe studies the universe using tools made of the universe. This does not mean that the universe intends to be understood. Intent requires agency, and physics offers no evidence of cosmic purpose. But it does suggest that understanding is possible because the universe is consistent, because its laws do not change arbitrarily, because patterns repeat across scale. If the universe were chaotic in a deeper sense, knowledge would be impossible. Questions could not be answered reliably. Experiments would not generalize. Observation would teach nothing. The fact that science works at all implies something remarkable about reality. It implies that the universe is not only lawful, but intelligible. This intelligibility has limits. Horizons block access. Quantum uncertainty constrains precision. Complexity overwhelms prediction. Not everything can be known, but enough can be known to build models that work, enough to send machines across the solar system, enough to detect ripples in spacetime, enough to reconstruct events that occurred billions of years ago. This partial knowability may be the most surprising feature of all. It suggests that while the universe does not owe us answers, it does not hide everything either. There is another layer to this question. Why do we care? Why should a temporary arrangement of atoms be motivated to understand cosmic history, fundamental forces, or the fate of the universe? Why not simply survive, reproduce, and vanish? Curiosity has no obvious evolutionary payoff at cosmic scales, and yet it persists. One explanation is that curiosity is a byproduct, a side effect of intelligence tuned for problem solving. Once a system can model its environment, it can model anything, including things irrelevant to survival. Another explanation is cultural. Knowledge accumulates, questions compound. Understanding becomes its own reward. Whatever the cause, the result is clear. The universe contains pockets where meaning is generated, not imposed from above, not written into the laws, but constructed locally by conscious systems interpreting their experience. Meaning is not a fundamental force. It is an emergent one. This does not diminish it. It makes it fragile. Meaning exists only while minds exist to generate it. When stars burn out and energy gradients fade, consciousness may disappear. The universe will continue, but without reflection. That possibility casts our moment in a different light. We are not just living during a readable era of cosmology. We may also be living during an era when the universe can be understood at all. That understanding does not belong to the universe by default. It exists because certain conditions temporarily allow it. This makes questions precious, not because they lead to final answers, but because asking them is something the universe can do only under rare circumstances. When you ask why the universe exists, or how it began, or what time really is, you are participating in a brief alignment between physical law and awareness. You are not separate from the cosmos asking about it. You are the cosmos, in one of its rare reflective phases, turning inward. That may not give the universe purpose, but it gives us one: to ask, to test, to understand as much as the laws and our limits allow, not because the universe demands it, but because, for a short while, the universe makes it possible. After everything we have uncovered, one question remains. Not a scientific one in the usual sense. Not something that can be answered with equations, observations, or experiments alone. It is the question that lingers once the facts have settled. What does it mean to exist in a universe like this? A universe without a center, without a preferred moment, without guarantees of permanence or purpose. A universe governed by quiet laws that operate indifferently, producing stars, galaxies, life, and eventually minds capable of wondering why any of it happens at all. At first, this picture can feel cold. There is no cosmic plan written into spacetime, no promise that complexity will endure, no assurance that meaning survives beyond the fragile window in which it arises. Everything that exists does so temporarily, balanced between emergence and decay, And yet, something remarkable follows from this. Meaning does not have to be granted from outside. It is created from within. The universe does not assign significance. It provides conditions. Under those conditions, matter organizes, energy flows, information accumulates, and eventually, experience appears. Experience changes everything. Because once experience exists, the universe is no longer just a collection of events. It becomes a lived reality, a place where moments are felt, remembered, anticipated, and valued. From the perspective of physics alone, a supernova and a sunrise are both just energy transformations. But from within experience, they are not the same. One inspires awe, the other marks continuity. Both shape how a conscious being relates to existence. This distinction is not written into the equations. It emerges, and emergence is the universe's quiet miracle. Across this journey, we have seen it again and again. Simple rules giving rise to complexity, gradients replacing sharp boundaries, processes unfolding slowly, patiently, over immense spans of time. The magnetic field that shields a planet, the layered interior of a gas giant, the long walk of light through a star, the hidden structure of a galaxy, the expansion of space without a center, the bending of time, the role of observation, the limits imposed by horizons. None of these phenomena were designed to accommodate understanding, and yet understanding happens. This suggests something subtle and profound. The universe does not need to care in order to be meaningful. Meaning is not a property of the cosmos itself. It is a property of the relationship between the cosmos and minds capable of engaging with it. When you look at the night sky and feel wonder, that feeling is real. It is not diminished by knowing that stars burn without intention. When you learn that time may not flow as you perceive it, your experience of moments does not vanish. It becomes more precious. Impermanence does not erase value. It creates it. A moment matters precisely because it does not last forever. A life matters because it occupies a narrow slice of time in an unimaginably vast universe. Understanding matters because it exists against a background of ignorance and uncertainty. From this perspective, science is not an attempt to strip the universe of mystery. It is an act of participation. Each measurement, each theory, each correction is a way for the universe to refine its own self-description, not perfectly, not completely, but enough to illuminate patterns that were once invisible. This process does not end with final answers. It ends only when questions can no longer be asked. And that gives our moment an unexpected weight. We live during a brief convergence, a time when stars still shine, when information still reaches us, when minds exist that can model reality and reflect on their place within it. This convergence will not last. Long after humanity is gone, the universe will continue expanding. Stars will fade. Galaxies will drift beyond one another's reach. Complexity will thin out. Eventually, even the structures that allow questions to be formed may disappear. The universe will not notice, but that does not make this moment insignificant. It makes it rare. We often search for cosmic meaning in permanence, in destiny, in something that guarantees importance from outside. But the universe offers something different. It offers possibility, the possibility for matter to become aware, the possibility for awareness to seek understanding, the possibility for understanding to shape how experience is lived. These possibilities do not require an external purpose. They are enough. To exist in this universe is to exist at the intersection of law and chance, necessity and contingency. You are the product of processes that began long before Earth formed, shaped by stars that lived and died billions of years ago. And yet, you are not merely a byproduct, you are a continuation. The atoms in your body were forged in stellar cores. The space between those atoms has been expanding since the universe was young. The laws governing your thoughts are the same laws governing galaxies. There is no clean separation between you and the cosmos. You are not an observer standing outside reality. You are reality, temporarily arranged in a way that can observe itself. That arrangement will change. It will end. Everything does. But while it lasts, It allows something extraordinary, the ability to know, not perfectly, not completely, but meaningfully, to trace origins, to question assumptions, to revise understanding, to stand under the night sky and recognize that the light reaching your eyes began its journey long before you existed, and yet arrives exactly when it can be perceived. In a universe without a center, you do not occupy a privileged position, but you occupy a valid one. Your perspective is not cosmically special, but it is real, and it is part of the same unfolding story as everything else. Perhaps that is the quiet resolution hidden beneath all the strangeness. The universe does not need a purpose to produce purpose. It does not need intention to allow intention. It does not need meaning to give rise to meaning makers. It only needs to be consistent enough, long enough, for complexity to emerge. And it has done that once, at least here. So when you ask what it means to be here, the answer is not written in the stars. It is written in the act of asking, in the willingness to look beyond immediate survival, in the patience to follow evidence wherever it leads, in the humility to accept limits without surrendering curiosity. To be here is to exist during the universe's reflective phase, a moment when it can, through you, wonder about itself. That may not last, but it is happening now, and that is enough.